Our next talk is by Ashwin Vasavada, who will be speaking to us about the value of integrating science and engineering teams in the operation of NASA's Curiosity rover on Mars. Take it away.
Hi, everybody. I'm the project scientist currently for the Curiosity rover. So kind of now for something completely different, but on the other hand, I think while maybe there won't be some things that are like literally applied to what you all are looking forward to in the future, I think a lot of the themes that we've already heard about today from various speakers will come up again, and you'll see how we've learned very similar lessons and, would really resonate with a lot of the same ideas that have been expressed. So, there's so many different things that I could talk about that we've learned over now about 16, 17 years in the development and operation of this mission. I've just chosen to focus on one fairly narrow topic, which is integrating the science and engineering teams and how much that's paid dividends for us. Next slide, please. So because we're not talking literally about astronauts on the moon or even Mars, but talking about a robotic vehicle operating on Mars, I thought I'd just tell you what I see as some of the relevant attributes where we have commonalities or differences. And one thing to point out is that we're doing a multi-year expedition on Mars using a robotic spacecraft. But, similar to what was described on the moon and what we'll see in the future on the moon and Mars, we're exploring a field site, and we're acquiring carefully selected samples and even analyzing those samples. And this is a scientific endeavor. NASA does purely technology demonstrations, but this is definitely a science-driven endeavor, and that's what a lot of this presentation is about. And yet, it's enabled by a complex and custom-designed piece of technology, the rover, and by the engineering that goes behind that. So there's a huge synergy that's already inherent in what this mission is, and we have to have a team and operations concept that's responsive to that framework. So to give you an idea, this is not a small thing. This is, of course, a multi-billion-dollar flagship mission. We have every day, it takes about 75 scientists and engineers in various roles in our operations process to operate the rover. The full team, which supplies those 75 that take different shifts, because we're a multi-year expedition, we don't have the opportunity to just bring everybody together in a room for 2 weeks or something. We have about 100 engineers and 500 scientists around the world who participate in the mission in various forms and take roles, take shifts, staffing the roles that fill the 75 seats that are needed every day. It's also an international mission, so our science team is 40% non-US, so which leads into the next bullet, which is, we have a partially co-located team. We do have a mission control, so to speak, at JPL, where the key operations personnel and systems are located. But largely, we operate with the majority of people remote. Another aspect of the mission that is relevant here is that we're pseudo real-time. We, of course, have the light speed delay from Mars. And we also are a multi-year mission again, so we don't try to stay in sync sleeping on Mars time anymore. We work on Earth business hours, and the way that usually works with Mars-Earth phasing is that we send between 1 and 3 days worth of activities each plan, and the rover autonomously executes those 1 to 3 Martian days worth of activities. So we don't operate the rover in real time like you might communicate with an astronaut on the moon, less so for Mars, of course. But we do, on the other hand, try to stay as real time as possible. We are highly responsive to the latest downlink. We sometimes only have 2-3 hours, to make scientific decisions, major scientific decisions, based on what we saw in the last downlink and send them back up. So that's not too different from what we saw in that awesome footage that was shown earlier. We have a lot of scenes like that in our science discussions. We are a strategically planned mission. As been mentioned, plans are hugely important, but you also have to be responsive not only to discovery as scientists, which can throw your plans for a loop, but also, of course, anomalies, as was also mentioned. And we're constrained by time, data return, energy, and safety. So to accomplish the science we want to accomplish, we're within a framework of a lot of constraints. And safety, for a $2 billion rover is already a pretty high level. And when you're talking about astronauts, I can only imagine. We've been on Mars for 8 years. We've traversed 25 kilometers, climbed 400 meters, and now successfully acquired 35 samples of Mars geological materials. Next slide, please. Okay, so just to point out that it's a complex spacecraft. We're accomplishing investigations with 10 different scientific instruments, as well as running a very complex robotic vehicle with a big robotic arm, a drill, and instruments that need to be placed very carefully by a large robotic arm. And we don't have eyes and ears. We don't have the situational awareness of a human. We do everything through the vision system and awareness that we can get from the rover itself. Next slide, please. I put this one in here because, as has been mentioned by others, it's important to know what your scientific goal is, and for the whole mission to buy into that and weigh every decision that's made against that. So we've had this sentence provided by NASA headquarters, since 2004, that we do really try to reinforce throughout the whole team and weigh all the decisions we make against. We have a scientific goal that we will explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, past or present. And when we come up with situations where we have to decide what takes priority, whether it's a scientific observation decision or even a risk trade, we have to weigh it against its importance to filling this primary scientific goal. Next slide. So some guiding principles, as I just mentioned, one is that our design choices, our mission plan, our landing site, and our operations concepts are all responsive to this overall mission science goal. And also, our mission success, for the reasons I walked through, it depends intimately, very closely on scientists and engineers working together in all project phases, in all the different relevant project subsystems, and at every level of decision making. And so, I have a very simplified version of our org chart to the right here, which shows, the top box of our project has a project manager and a project scientist. The project scientist isn't in some lower stem winder somewhere, he or she is right up there in the top box. And just to reinforce that, I put the picture of the project manager and project scientist we had by the time we launched. I'm now the project scientist, of course, but this is the two folks that were in those roles. And, just to reinforce, they were a team. They worked together throughout the development. They were there in front of the TV cameras the day we launched. And then also, this is something that I worked very hard on personally to enforce within our project. I've seen the same term used in other Apollo presentations, which is awesome. And I wish I would have been a better student of Apollo before I started this job. But we felt that JPL really wasn't doing enough here to embed scientists within the engineering teams. So we worked very hard in the early days of Curiosity to do that, to really force the people who are designing things like the rover's drill, the wheels, all those sorts of things, to have a scientist at every one of their meetings. Even if they were quiet most of the time as engineering decisions were being made, they could speak up when necessary to enforce science objectives, and very importantly, to interpret science objectives, to give nuances about them, and to provide expert advice in real time. Next slide, please. So now I'm just going to walk through very briefly a couple specific examples. Now, these aren't real-time operations examples. I apologize for that. These are more about the development process of our mission, but I think the message is the same. So landing site selection was a multi-year process that occurred in parallel with the design of the landing system, the crazy one that you just saw work for a second time with Perseverance. And it also occurred in parallel with orbiter data sets that were being acquired. So, over the 6 years this occurred, the engineers were literally designing the landing system, and the scientists were, literally getting new data from Mars that informed the process. So we had a iterative process over those 6 years where the engineers would brief the wider science team on what the system's capabilities were. The scientists would look at the places on Mars that were consistent with those capabilities and push back if we couldn't get to some places that were truly important. I think Jim had mentioned places, that had a lot of boulders. It's a classic example. But, the other attributes are things like latitude, elevation, terrain roughness, traverse distance, all those things, when it was an iterative process that produced the best landing site when we weighed those various constraints against the capabilities of the system. Next slide, please. Similar for the landing process itself, I just mentioned the terrain side. We had an atmospheric side, obviously not for the moon, but for Mars, landing a very complex system required a very precise and state-of-the-art understanding of the atmosphere of Mars. And so we formed a working group of atmospheric scientists to produce that data and interpret that data and make sure the data was used in the appropriate ways by the engineering team who was designing the hardware. And that was extremely important, and those scientists also had to learn from the engineers how the system worked, what its vulnerabilities were, so they could understand how to produce the best data to help them with their task of designing the system. So again, we needed to have scientists and engineers working intimately together from very early in the mission's formulation. Next, please. This is our equivalent of a field test where we take the robot out and, it looks stripped down because we had to make one that has the same weight that it would have on Mars and 1/3 gravity. So this is Curiosity out in the Mojave Desert on the top photo. And again, bringing together the designers of the mobility system, geologists who could, understand what the best analog sites were that we'd find on Mars, and terramechanics experts, so kind of a engineering science combination expert, people who understand how wheels interact with geological materials, that sort of thing. So again, forming these combined teams of scientists and engineers to solve these issues together and understand each other's points of view. Same thing happened later in the mission when we had wheels that developed tears and holes in them unexpectedly. We had to form a working group to solve this anomaly, again, with scientists and engineers, scientists who could look at the geological materials on Mars that were causing the problem and figure out how to maybe avoid them, and engineers who understood the wheels and the hardware that was interacting with the rocks in a way that caused these problems. And together we found the best solution to which now has mitigated this problem. And we have a real-time terramechanics expert, not real-time, I shouldn't use that word when you're talking with you all, but for us, what I mean is ongoing effort by a terramechanics expert to simulate past drives and update the engineering team on the scientific analysis of how the mobility system has been performing on Mars. Next, please. Tactical planning, here's where we're talking about operations. We have planning accomplished by what we call the Science Operations Working Group. That includes everyone, including what, on a lunar mission might be called like the flight director. That our process is led by a tactical uplink lead, who is that flight director kind of person. But the working group as a whole is chaired by a scientist, who leads the negotiations of how rover resources are used. So every day on Mars, while the tactical uplink lead is overseeing the process and has ultimate authority over the safety of the rover, et cetera, a scientist is the one who's taking all the inputs from the engineering team and the science team about what the rover's tasks are and how we're going to use resources to plan out each day of the rover's activities. We do have scientists who have their own virtual meeting rooms, geological focused, et cetera, where they can be offline and having more detailed discussions. but we also have all the screens in our main operations area and voice lines open to the entire science team, and a few selected scientific representatives who interface directly with the engineers as they command the rover. Next slide, my last one. Sorry, I'm a few seconds behind here, but this is just a summary. You know, our success depends on bringing technical and scientific expertise together to make informed and timely and balanced decisions. You have to build that culture. It doesn't happen automatically. You know, it takes people like Gene Shoemaker and others to work with institutions, and setting that culture from the top down is the best way to go. You know, we need to try to be firm about having science representation wherever decisions are made, and some of the previous talks really have shown that, which is wonderful. We want to appreciate each other's different contributions, but work together and cultivate interactions that build trust between the teams. And I think I'll stop there since I'm over time, but you can, of course, read the rest of these bullets. And thank you.
Thank you, Ashwin. That was really interesting. It's great to see how robotic exploration has lessons that human exploration can learn from.